We will continue our discussion on OSPF in today's class. Right. Now, in the last class, we did a small practical of OSPF between two routers, and we just saw how the two routers are exchanging their information to each other, the links that they are connected to each other. Right. This is what we learned. Right. Now, if you remember our discussion on the interface, if you remember our discussion on the interface, we know that the serial interface as per OSPF is called as point to point. Right, this is what we had discussed uh, in a couple of earlier sessions. Right, serial interface as per the OSPF is called as a point to point. Right? So over here on R1, okay, on R1, let's check those OSPF interfaces. So to check the interfaces on which OSPF has been enabled, you write the command show IP OSPF interfaces. All right. Now over here, we can see OSPF has been enabled on three interfaces. Okay, three interfaces. One is the loopback address 1.1.1.1. The other is the other loopback address 1.1.2.1, and then the uh, 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 serial interface 12001. And if you see the serial interface 4/0, right here, you can see that the network type is point to point, is point to point. Okay, and the cost, the OSPF cost for a serial interface is 64. Is 64. Similarly, if we remember, we were discussing that the OSPF finds out the shortest path using a parameter called as link bandwidth. And here the link bandwidth is basically what the cost we are talking about. Okay, it is the cost. Okay, so the link bandwidth. Okay, the link using this link bandwidth. Okay, a link to find out the cost. The formula is 10 power 8 divided by the reference bandwidth. Okay, 10 power 8 divided by the reference bandwidth. Now, 10 power 8, okay, or not 10 power 8, sorry. Yeah, not reference bandwidth. 10 power 8 is the reference bandwidth divided by the link bandwidth. Okay, this 10 power 8 is called as the reference bandwidth. All right. So 10 power 8 divided by the link bandwidth will give us the cost. Okay. And over here, the cost of a serial interface is 64 kbps. Okay. And this is 10 power 8. Okay. 10 power 8 kbps. Sorry. 10 power 8, which basically is 100 mbps. Okay. So it's basically your 100 mbps divided by 64 kbps. Okay, this is 110 power 8 kbps, which if you convert it into megabytes, it will be 100 mbps divided by 64 kbps, which will basically give us 64. Okay, the cost as 64 kbps. Now, that is what you see over here, the cost as 64. All right. And for loopback addresses, the cost is 1. Loopback address, another, the cost is 1. So the cost that I was talking about when OSPF calculates the shortest path to a particular destination through the link bandwidth or through the cost. The cost that I was talking about is this cost that the OSPF has calculated using the link bandwidth. All right. Okay. So I would like to reiterate or rephrase my statement over here. So the serial link that we were talking about, okay, that we have been talking about, actually the serial link consists of multiple 64 kbps links, and when they are bundled together, they give us a speed of 1.4544 mbps. Okay, so it's not 64 kbps. One serial link has multiple links of 64 kbps each, and when they are joined together or bundled together, they are the total bandwidth that you get is 1.44 mbps, meaning like suppose this is one cable, okay, and inside there are different small wires, okay, and each wire's capacity is 64 kbps, okay. So when you add them together, you get 1.544 mbps speed. All right. So this 64 kbps is basically your reference bandwidth, that is 100 mbps. Okay. That is basically your 100 mbps, 100 mbps divided by 1.544 mbps, which gives us 64, which is basically your 64 over here. So loopback it thinks loopback address as having 100 mbps speed. So 100 mbps divided by 100 mbps is 1, right? So what basically is happening here is that OSPF pre-calculates these costs. OSPF pre-calculates these costs of each and every interface. Okay, and how does it find the shortest path to a particular destination? Let's check that. Okay, I'll just give you an example of how OSPF finds out the shortest path towards a particular destination. Okay. Now, if I enable OSPF between R1, R2, and R3, from R1's perspective, to reach R2, it has two paths. One is this direct path, the other is this indirect path. Right. Now, consider this as a 100 Mbps link. This also has 100 Mbps. This as 100, or all the interfaces having 100 Mbps speed. Okay. For R1, okay, to reach R2, what will be the cost? We know that cost is calculated based on the reference bandwidth divided by the link bandwidth, and link bandwidth is also 100 Mbps. So that gives us 1. So all the interface costs on each of these links is 1. And OSPF always uses the outgoing cost to reach a particular destination. Okay, so in this scenario, for R1 to reach R2, the outgoing cost over here is 1. Okay, then for R1 to reach R2 via R3, what is the total cost? The outgoing cost over here 1 plus R3's outgoing cost to reach R2, that is 1. In total, the cost is 2, right? So obviously 1 is lesser than 2, and hence the lower cost path is always preferred by OSPF. And this is how OSPF finds out the shortest path to reach a particular destination from a source using the cost. And we know how cost is calculated. 10 power 8 divided by the link bandwidth. Okay, now you may also think, or you may think, this is only a 100 Mbps link. Okay, we have seen there are links which are 1 Gbps, 10 Gbps, 100 Gbps, or 1000 Gbps. In such a scenario, what is going to happen? Okay, because 10 power 8 divided by 1 Gbps. 1 Gbps is basically 1000 Mbps. Okay, so it's basically 10 power 8 divided by 10 power 9. It's basically like this. 10 power 8 divided by 10 power 9. So you will get a value which is in negative, right? Which is a negative. OSPF does not consider negative values. It will always consider negative values as 1 only. So no matter. So in this example, let us take this particular example, R1. Okay, here it is R2, R3. Okay, think that R1 and R3, these interfaces, for example, are 10 Gbps links. 10 Gbps links. Obviously, 10 Gbps links are faster than a 100 Mbps link. But as per OSPF, 10 power 8 is the reference bandwidth that it uses divided by your link bandwidth. Correct? So for an 100 Mbps link, it will be 10 power 8 divided by 10 power 8. That gives us the value of 1. For a 10 Gbps link, it is going to be 10 power 8 divided by 10 power 10, which again goes into a minus value. Okay. And as I said, for a minus value, the not the router, the OSPF considers a minus value as 1. So the thing is, though this link is faster, okay, from R1 to R3, this link is faster. But based on the calculation or based on the limitation of the calculation that OSPF has with respect to the reference bandwidth, the shortest path for R1 is still this one, the slower path. Okay, I hope you're getting this point. From R1 to R3, this link is 10 Gbps, and this link is also 10 Gbps. Obviously, 10 Gbps link is faster than 100 Mbps link. So even if R1 chooses this longer path, it will be faster. It will be faster than the direct path. Okay, but because of OSPF's cost calculation, any link which is higher than 100 Mbps of bandwidth, the cost will remain 1. Right? So there you have a limitation. What about links that are higher than 100 Mbps? We have links higher than 100 Mbps. For them also, the OSPF is going to calculate the cost as 1 only. That is why we have this is a reference bandwidth. As I said, this is a reference bandwidth, which is 10 power 8 divided by link bandwidth. So based on your link bandwidth, you can change your reference bandwidth as well. If your link bandwidth goes beyond 100 Mbps, for example, if your link goes beyond 100 Mbps for say 1 Gbps or 10 Gbps or 100 Gbps or even 1000 Gbps link, okay, you can change your reference bandwidth value as well. This is the, or you can call this as the default reference bandwidth value. You can change this default reference bandwidth value to a higher value as well. Okay, you can go for 10 power 9 or 10 power 10 or 10 power 11 or 10 power 12. Okay, based on the bandwidth or based on the link bandwidth that you have, you can change your reference bandwidth, and based on that, now the OSPF will have new values. The OSPF will have new values. Okay, so let's imagine that your reference bandwidth is now 10 power 10. Okay, your reference bandwidth is now 10 power 10. So what is going to happen? Okay, 10 power 10 divided by 10 power 10, you get 1. All right. So for these links, which are 10 Gbps link, you get one value, one value, one value, and one value. What about this link? Okay, which is basically your 10 power 8. Okay, so you have 100 as the value. Okay, you get 100 as the value. Okay, so obviously 100 is higher than, okay, so the cost from here is 2, but the cost from here is 100. So obviously OSPF considers a lower cost path than a higher cost path, and hence this particular path will be preferred based on the higher bandwidth of the link. So this is how your OSPF calculates the cost. Okay. Now with that, we also know how and why OSPF considers, or how OSPF thinks serial interface as point to point and loopback interface as loopbacks, or stub. We can call it as stub as well. Okay, loopback interfaces are loopback. Serial interfaces are point to point. Okay. Now continuing our discussion from last few classes. Today we will discuss further on Ethernet interfaces. And when we were discussing the Ethernet interface, we discussed OSPF considers Ethernet interfaces. Okay, Ethernet interfaces as broadcast interface. Okay, I will show you the network type of a broadcast or an Ethernet interface when we do the lab. Okay, So Ethernet interfaces as per OSPF are broadcast interfaces. And again, let us have a small discussion of why does OSPF considers Ethernet interfaces as broadcast is because Ethernet, by the name, we know that Ethernet is a big part of something called as a LAN, local area network. And we know how to create a local area network. Okay, we can connect multiple devices with a switch by and create a LAN of itself, a local network of itself, right? So for Ethernet or for OSPF, Ethernet means that interface will be connected to multiple devices, not just one single device as in serial interface. So R1, okay, when R1 was connected to R2 using a serial interface, okay, it was called as a point to point, right? For if R1, okay, is connected to R2, okay, using an Ethernet interface like fast Ethernet 0/0, although there are only two devices connected on this link, OSPF will still think this as Ethernet or a broadcast link. For OSPF, Ethernet links are broadcast interfaces, meaning that OSPF thinks OSPF does not have visibility of what devices are connected beyond this interface. After this interface, how many devices are connected? OSPF does not have that visibility. OSPF only knows that there is some connectivity out of this interface. Is it connected to a single router? Is it connected to multiple routers? Is it connected to only two routers? Or is it connected to all routers in the network? It does not have that visibility. But because it's an Ethernet interface, and for OSPF, again, it thinks Ethernet interface means it is connected, that interface is connected to multiple devices or multiple routers or multiple routers. Got it? Now, again, let us assume from OSPF's perspective. From OSPF's perspective, it thinks that an Ethernet interface is like this. Many routers will be connected on this particular link because it's a LAN interface like this. This is what it thinks. It, as I said, the connectivity may be just like R1 and R2, but for OSPF through an Ethernet interface, or Ethernet interface. For an OSPF, it thinks Ethernet interface as a LAN interface, meaning there are multiple routers connected on that interface. So now let's think from OSPF's perspective. Let's start thinking from OSPF's perspective. What if OSPF is right? Or what if we have such a scenario where R1, R2, R3, R4, they are connected through a switch with an Ethernet interface? Now, in such a scenario, how is OSPF going to work? Okay, for just two routers, R1, R2, okay, with R1 and R2, what happened? R1 and R2 will form adjacency. They will form adjacency. All right. Now, over here, with four devices, R1 is going to form adjacency with R1 is going to form adjacency with R2. R1 is going to form adjacency with R3. R1 is going to form adjacency with R4. Similarly, R2 is going to form adjacency with R4. R2 is going to form adjacency with R3. R3 is going to form adjacency with R4 as well. So what is happening? Four routers, okay, each router, one router is forming adjacency with three other routers. That means four routers will have three adjacencies, or in total, they will have 12 adjacencies. Between these four routers, there will be 12 OSPF adjacencies. 12 OSPF adjacencies. All right. Now, why is this important to understand? Or you may think, okay, even if they have 12 adjacencies, what is the problem? The problem is, let me take you to this particular diagram, this single diagram. So, as I said, when we were discussing the OSPF states, if you remember, I mentioned that the two routers will exchange the database. They will exchange the database of their links that they are connected to. They will exchange the database of the links that they are connected to, right? Database. Now, to check the database, all you need to do is show IP OSPF database. Okay. So you will see this is a database. We will discuss this database probably later. Okay. Or because this is just a normal, or this is just a very beginner OSPF level, probably I will not go in depth about this database part. If you want to understand how OSPF works in data from database perspective, you can buy my CCNP course, okay, which is basically in depth about how OSPF works, what are these databases, etc. In depth. All right. Now, anyway, as I said, I will not be, because this is basic to advanced, and I'm still trying to stick to the basic level so that everyone can understand. That is why I'm not going to go in depth about this database. And if anyone is interested to know in detail about this database structure, you can go through my course of CCNP plus CCIE course. Okay. So there I have explained in depth about how database works. So you can see here this database. Okay. You will find an exact copy of this database. You will find the exact copy of this database on R2 as well. Show IP OSPF database. You can find the exact copy of this database on R2 as well. So what is happening? R1's database is just an exact replica of R2's database, or they both have a replica of their database with each other. So why is this important? Why do they have a duplicate database with each other? The reason is, the reason is that is how OSPF basically works. Okay. So OSPF is called as link state protocol also. It's called as a link state protocol. Now, what does a link state mean? We just discussed, okay, we just discussed that in our previous session of lab, R1 was sharing or advertising its network to R2. Okay, R1 had two networks, two loopback addresses. Okay, R2 also had two loopback addresses. Okay, 1.1.1.1 and 1.1.1.2. And R2 also had 2.2.2.1 and 2.2.2.2, right? And 12.0.0.1 and 12.0.0.2. These were the IP addresses. And what was happening? R1 was sharing information of each and every link that R1 is connected to, and it was sharing this information with R2 and vice versa. It was happening, right? And it may not seem a big deal for you when you just have two routers. What if you have multiple routers? You have R3 connected, okay, you have R4 connected, okay, then R4 is connected to R5, R4 is also connected to R6, okay, then R4 is connected over here to R1, R4, R6 is connected to, let's say, R3, okay, R6 is then connected to R7 over here, okay, R7 is connected to R1, R7 is connected to R4. Let's imagine you have such a network, okay, and you want the reachability of each and every router, and you want that each and every router share their routing table information with each other. And we know that why is that necessary? Because if R1 wants to send a data towards R5, information of R5's network should be present in R1's routing table. Then only R1 will be able to send the data to R5. Correct? I hope we are clear with this part. And when OSPF is enabled on all the routers over here in this network, what is going to happen? They will exchange their database information. Okay, they will exchange their database information with every router. So when I enable OSPF on R5, R5 is going to share that information with R4. R4 is going to share that information with R6, R7. Okay, and over here R3 as well. R7 is going to forward that information to R1. Okay, R6 is going to forward that to R3, R3 to R2, R2 to R1, etc. They will all of these routers will share their link database information with each other. All right, thereby populating their routing table. Okay, now imagine this part where R1, okay, where okay, so when they have exchanged their database with each other, what is going to happen? I just showed you that with two routers, R1 and R2, they both have duplicate database. Okay, and first of all, as I was telling, why is it important? It is because from R1, from R1, I know how is R4 connected. From R1 itself, on R1's OSPF, looking at R1's database, I can tell how many routers R4 is connected to. Okay, how many routers R4 is connected to? What are the IP addresses that R4 is connected to? And what is the cost of those links that R4 is connected to? I can check all this information by checking or like executing the appropriate command on R1. Okay, this is what you call it as.
No, but that has to be that the links R1 knows about R4, the cost of the links. And those links are like from R1 to R4 reaching links. Those cost or because R4 might not connect from all of the links back to R1. It might be R4 to R5 and go somewhere else. That also R1 will know. Only R1 can reach through various ways to R4. That much only it will.
No, it will know how to reach R4. See, for R1 to reach R4, it will know how to reach R4 via different paths. It will know how to reach this, this, this. It will also know how to reach this, 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 and this. It will also know how to reach here. It will also know how to reach like this. It will also know how to reach this. It will have every view, and that particular view is called as topological view. Topological view.
Okay. And for R5, it will also know the route to R5 or
Yes,
till R4
yes,
only it
yes.
will know and
Not no no
R4
no.
will know the route to
I
R5.
just gave you an example. I just gave you an example of R4. R1, not just R1.
Okay.
Every router in this network will know how to reach each other. And what is how to reach each other? How how many routers are every other router connected to? What are the costs? What are the IP addresses? What are the link? Are they serial link? Are they Ethernet link? Are they loopback addresses? Every information, that database that I was talking about, the database is exchanged in the loading phase. When the loading phase, when the two routers, any two routers are exchanging their database, they exchange all this information as well. So what is happening? Let's say between R4 and R5, we create OSPF, they exchange their database. So R4 and R5 are not connected. When between R7 and R4 that OSPF happens, R4 will share R5's database with R7 as well. Okay. Now, when OSPF happens between R7 and R1, R7 is going to share not only his database, he is going to share R4's database, he is going to share R5's database as well. So in this way, every router, when they are completely connected through OSPF, all the routers in the network will know about each other's database. Thereby, thereby they will have the whole topological view of the network. This is the main advantage of using OSPF. This is the main advantage of having OSPF.
So too much data size that disk size also will be required to store a lot of things plus lot of traffic already it will consume for this.
Correct. See, the thing is, see, database does not consume too much. thing. Okay. So yeah, as you said, it's correct. As you said, it is absolutely right. Okay, we will talk about that probably in the next few classes. Okay, you're absolutely right. The database consumes a lot of memory. It will create a traffic congestion if not properly handled. We will come to that part. Okay, you pointed out exactly a good point, which probably may we will discuss tomorrow or day after. All right. Now, as I said, so with OSPF being a link state protocol, every router gets a topological view of the whole network. All right. Now, as I was discussing, when all the routers have the topological view of the whole network, meaning that all the routers in this particular network, in this particular small network from R1 to R7, R1, R1 will have the database information of R1 to R7. R2 is going to have the database information from R1 to R7. R3 is also going to have the same. R4 to R7, all of them will have the database information of all the routers in the network. Okay, this was my point to explain this whole process. All right, now coming back to our discussion on the Ethernet link, OSPF, OSPF on Ethernet link. Okay, Ethernet interfaces. Now, as I said, for OSPF, an Ethernet interface is an interface. It assumes that that interface is connected to multiple routers through a switch. Or let's imagine that there is actually a topology where multiple routers R1, this is a switch, R2, R3, and R4. You have four such routers which are connected to each other through a switch. So over here, as I just explained, R1 is going to have adjacency with three routers, that is R2, R3, and R4. Similarly, there are four routers, they will have three adjacencies each, thereby having 12 adjacencies. In total, there will be 12 OSPF adjacencies. Right? Now, this is not a problem. The problem is R1, as I said, R1 will have the database of all the routers, that is R1 to R4. R2 will also have the same database, R1 to R4. R3 is also going to have the same database, R1 to R4, and R4 is also going to have the same database as R1 to R4. Right? Any changes that happens in between these four routers. For example, let's say I add one network. Let's say I add one network over here. For example, 1.1.1.1. That is a kind of a change in the network, or that's an update for R1. What R1 is going to do? R1 R1 will share this information with R2. It is going to share that information with R3. It is going to share that information with R4 as well. Now, as I said, one router is sharing that information with three routers. So every time R2 receives this information, R2 will when R2 receives this information with R1, R1 R2 is going to share that information again with R2 and R4 and R1. R3, upon receiving this information, will again share that information with all the routers. So what is happening? You have the same information. Every router is sharing the same information with each other. What is the point? And all of them are connected to the same network. We are talking from a LAN perspective. We are talking from a LAN perspective. When we are talking from a LAN perspective, they are from the same subnet as well. They're not from different subnet. They're from the same subnet. Okay, so any information that is new to a network or any changes in the network, all the routers will share this information with each other, and then again it goes as a nuclear reaction. Every router will share that information with each other, then it goes to other router, then they will share. Eventually what happens, all the routers will fall back to the same database. R1 will update his database with 1.1.1.1, and every router will update their database with the additional network of 1.1.1. So here what is happening? you have 4 duplicate database. Correct? You have 4 duplicate database. In our previous example, please remember, none of these routers are connected through a switch. None of them are connected through a switch. It's a direct link between two different routers. So the OSPF messages that we are talking about over here, okay, any update, for example, okay, any update, okay, any update, okay, will or will be passed on only to R2, and or from R1's perspective, let's say I add some network, okay, let's say 1.1.1. So R1 is going to share that information to R2, R2 is going to share that to R4, R1 is going to share that to R7. Okay, then R7 will forward that to R6. That's it. It's not going to go as a nuclear reaction. It's not. Eventually, the update will happen with all the routers, but it's not going to explode like a nuclear reaction. Over here, it explodes like a nuclear reaction because you have a switch in between. R1 will share that information to R3. R1 is going to share that information to R2. R1 is going to share that information to R2. See here, R1 has already shared that information to R2. Why is there a need for R3 again to share that information to R2? Or R4 to share that information to R2? Or R4 to share that information to R3 and R3 to R4? What is the need? There is no need for it. So it's going to explode like a nuclear reaction when you have a switch in between. Okay, so here what happens is that, so adjacencies are already there, but what happens? Your exchange of information because of a database change explodes, and you do not want that. Okay, it's not a big deal. Honestly, it is not a big deal. However, if you have such a scenario with huge network, you have a lot of routers, you have a lot of switches involved, and when you enable OSPF, it's going to explode. I do not want that. Okay, so for this purpose, what we thought is, if we have, obviously we are going to have duplicate database, right? All of the routers you can see here, R1, R2, R3, and R4 will have the same database, right? We just saw this example over here. Why can't I do one thing where I make one guy over here, for example, R1 as the, let's say, a master. Okay, he, with the master, all the routers will create adjacency. R1, R3, R1, R2, and R1, R4. So over here, what is happening? The master only is having an OSPF adjacency with 3 routers, but the rest of the 3 routers will have adjacency only with the master. That is only one single router. So in total, instead of 12 OSPF adjacencies, you just have 4 OSPF adjacencies. You just have 4 OSPF adjacencies. Are you with me till here?
No, how it is four? There is one from
the
R1 to
the
R3, one from
our
R1
master.
to switch.
Hmm.
So R1 to switch, and then R1 to R4, then R4 to switch, R3 to
Okay,
switch, and
or
again
okay,
R2 to switch.
or just not 4, just 3 in total. 3 adjacencies. Okay, R1 to R3, R1 to R2, and R1 to R4. Only 3 adjacencies are there.
And R3 to R4.
No, that's what I said. That is
Oh,
that is what the thing is. I will have adjacency only with the master. Let's consider R1
no,
as the master router.
what do you mean by what do you mean by the adjacency?
Adjacency mean OSPF adjacency. We saw there was a two-way neighborship and then there was a full. When I say adjacency, it means the full state, forming a full state where the two routers have exchanged their database, the whole database.
Okay. Okay.
Okay, they have exchanged the whole database. Okay, so R1, the master, is going to share or exchange the whole database with R2, R3, and R4. And yeah, obviously R4, R4 and R1 has adjacency, R2 and R1 has adjacency, R3 and R1 has adjacency. Okay, so instead of 12 OSPF adjacencies, you just have 3 OSPF adjacencies. Okay, now what is happening over here? Even though you have 3 adjacencies, the database remains the same. The database will remain the same. Why? I'll give you an example. Let's say I add some network over here, for example, X network. I add some network, X network on R2. What is going to happen? As I said, the adjacencies that are formed are only between the master router and the other routers. R2 is going to share this update only with the master. Okay. R2 is going to share this update only with the master. Then what the master is going to do, master will forward this update to R2, sorry, R3 and R4. Thereby, now the new update of X network is in the database of all the routers.
But
Got
this
it?
will go through the switch only. Right? There is no connection direct between R1 and R3. So even if the master sends R1, it will go to the switch, and the switch will forward to R2, R3, R4 everywhere. So there is no direct
Yeah,
connection, right, between the
yeah,
R1
yeah.
and R3 and R1 and
You are
R4.
absolutely
So if
right.
it goes to the switch, it will pass it to everybody. Right? Same case.
Yeah, yeah. I'll tell you how it happens. Yeah, I'll tell you how it happens. Okay, don't worry. Your confusion is absolutely right. Okay, I don't deny that. You're absolutely right. So no, I was saying if there was such a scenario, okay, where only the master will do the advertisement of the database, it's good, right? It is good. So over here, as I said, we will create one master, one router as the master, and he will have adjacency with the remaining routers. And the remaining routers will share their updates with the master only. No other routers will, like non-master routers are not going to share their adjacency with, not adjacency, their database with themselves or between themselves. Okay, this is what we wanted, and we created such a feature. Okay, and that feature is specially, as I said, is specially is a special feature created only for Ethernet interfaces, only and only for Ethernet interfaces. Okay, so in this case, what happens, that master that I was talking about, the master is called as the designated router. It's called as the designated router. And the designated router is the router which has the highest router ID. The router with the highest router ID becomes the designated router. So in our case, if we take 1111 here, this is 3, this is 2, and this is 4. So in this case, R4 becomes the designated router. R4 becomes the designated router. So R4 is going to form adjacency with R1. It is going to form adjacency with R4. Sorry, R3. It is going to form adjacency with R4. Any update in the network, any update in the network will be sent to R4. Now you may ask, how? How is that possible? Okay. So if you remember when we were discussing the hello messages, when we discussed hello message, okay, we saw that the hello message was sent at a destination IP, which is a multicast IP address of 224.0.0.5. Okay, this multicast address is all OSPF routers, all OSPF router multicast address. So any message that is sent at this particular multicast address will be heard, listened, and received by the routers that can understand OSPF messages. Okay, so this multicast address is used by all OSPF routers who can understand and receive or send messages about OSP. All right. Now, if over here, if I, let's say on R2, as I said, I bring up one more network, 2.2.2.1, for example. So if R2 still uses 225, not 225, 224.0.0.5 multicast IP address as the destination IP address, as the destination IP address, R2 will send this update to R3, is going to send to R1, it's also going to send to R. Then what is the purpose of the designated router in this scenario? What is the purpose of designated scenario or the designated router? The deal was R2 should send this update only to the designated router. It should not send the update to every other router. But because OSPF is using 224.0.0.5, which is all OSPF multicast address, R2 will send this update to every other router as well, even though there is a designated router. Right. So for this purpose only, we created one more multicast address that was 224.0.0.6, which is only DR multicast address. Only DR multicast address. Okay, only DR multicast address. So here, what will happen is when I add a new network 2.2.2.1, for example, what R2 is going to do, R2 will send this update at the multicast address of 224.0.0.6, which will be only heard, listened, understood by DR only. So in our scenario, DR is the R4 is the DR. So with a switch in this particular scenario, this 224.0.0.6 will reach R3, will also reach R1, will reach R4 as well. However, 224.0.0.6 is a DR only multicast address. And since R1 and R3 are not DRs, they will not accept this message or update. The update will be learned only by R4. Are you with me till here?
Yes, still this they got. Only the doubt was the switch will not cause any problem because if it was direct connections, it was fine.
Sorry, you were saying something?
Yes, I was telling this switch is there in the middle, right? If the
Hmm.
connections was between the routers, it was fine. But
Hmm.
now since the switch is there, it won't understand any multicast or anything, right? So what will happen if
Correct.
R2 sends in any multicast? Anyways, it is not going to go to only R4. It will anyways go to this also. So it
Yes.
will be still that broadcast kind of thing only, right? So it will go to
It
everybody.
exactly. It will go to everybody.
But
However,
but they
because
but they will not but they will not reply.
they will not even
They
accept
will not
that
reply
message
back.
because they will not reply back. They will not even receive that message because the multicast address is at 224.0.0. For them, this multicast address is an unknown multicast address, and I'm not going to entertain any unknown IP addresses.
So
Okay.
only one side only the flow will be there, other side will not come.
Yes. Yes. So over here, what will happen? R1 and R3 are receiving those messages or updates, but because they are not DRs and only DR can understand 224.0.0.6 multicast addresses, it will be the only router that is going to listen to this update that is sent by R2. Okay, are you with me till here?
Yes, yes, it's clear.
Yeah. Now what is going to happen? R3 and R1 still do not know about 2.2.2. The database, as I said, the database has to be same. in OSPF network. That is the purpose of OSPF. The database on all the routers should be same in the network. Now what R4 is going to do? What R4 is going to do? R4 is now going to send this update, okay, to all the routers with the multicast address of 224.0.0.5, which is all OSPF routers, which is all OSPF routers. And hence, here what is going to happen? R1 and R3 now will know about the new link of 22221 in there, and they will add this in their database as well. So now what happens? All their database is now same. It's synced. So any update from non-DR routers, any update that is sent will be sent at the multicast address of 224.0.0.6, which is only DR multicast address. When this update is received by the DR, it will spread this, or it will send this update to all other non-DR routers at the multicast address of 224.0.0.5, which is all OSPF multicast. Got it? And this is how your flooding flooding of updates is stopped in a Ethernet environment or a LAN environment.
So
Got
this
it?
whatever R2 send the data to R4, so that thing
Hmm.
data when R4 sends to the multicast, that will again received by R2 also,
Yes,
along with
it will be
R1
received,
and
but
R3.
however, because
It has already has the data.
it already has that entry, it will not make any change. It will not make any change. Okay. Now, what if what if R4 fails? Okay. What if R4 fails? R4 is supposed to be the designated router. With R4 only, every router will make adjacency. Okay. So previously, what was happening? R1, R1, R2, and R3 were having an adjacency with R4, but R4 is no more. If R4 is no more, any update that is sent by R2 or any other non-DR routers will again cause a flooding. Okay, because this 224.0.0.6 is multicast address, which is heard only by DR, is no more. Right. So this update that is sent by R2 will be again, it will not be updated on R1 or R3. Okay. So for this purpose, we created one more router called as backup designated router, or BDR, which is basically your second highest router ID. Second highest router ID. So in our scenario, R3 over here, R4 becomes your DR with 4.4.4.4 as the router ID, and R3, which is the second highest, it becomes the BDR. So what is going to happen? What is going to happen is that if for some reason, if DR fails, if DR fails, okay, the BDR will immediately become DR. BDR will become DR, and it will it will ask all the routers to share their database with R3. Okay. Now any update that happens in the network, let's say R1 now gets a new link, for example, X. Now R1 will send that update to R3. R3 will forward that update to R2. Okay. Any question?
No, yes, I got it.
Okay.
So this
So
will
we'll
not
stop.
be an
Yeah,
actual
yeah.
situation, it switches, or it like another real scenario with this routers will connect to routers only, or switches also will be there in the connections.
Switches will
Here
also
for
be there.
demo you showed a switch with. Okay, switch
No, no,
also
no.
will be there,
Switch.
router also will be
Yes, yes, yes.
there.
Yes. Okay. So with this, I'll stop our session today and we'll continue our discussion on this DR and BDR tomorrow.
Okay, sure. Sure.